So the heating curve will put our pieces together of calorimetry and delta H all in one place. So heating curve determines the amount of heat it takes to go from, let's say, a solid to a liquid to a gas. And so it's not a single step that we can do. It's actually multiple steps that have to be added together. And it has to do with the heat differences of going to the different phase changes and then our different heat capacities depending on the different states of matter. We do have to keep units consistent. Okay, so a lot of times calorimetry is going to be in joules and our delta H problems are in kilojoules, and we need to make sure they're in the same unit. Sloped lines are calorimetry problems and flat lines are molar enthalpy problems. So if we look at a typical heating curve, you'll notice time on the bottom and temperature on the other axis. And you'll see on this example, we're going from minus 80 all the way up to, let's say, 140-ish. So if you'll notice these sloped lines, it is a calorimetry problem. So that's usually written as we would write it in class as Q equals MCAT. Now our flat line is a delta H problem. Notice this is the molar heat of fusion. So this has to do with our freezing point. So notice it's right at 0 degrees C. Again, we have another calorimetry problem. So Q equals MCP delta T. And notice that our heat capacities do change depending on the state of matter that we have. Now this next flat line would have to do with our boiling point, and so that is why it's the molar heat of vaporization. And so if I asked you to draw a curve like this, you would note that 0 and that 100 degrees C, you'd want to keep that consistent. And then we can do calorimetry here as well. So we wouldn't necessarily have to always go from the bottom to the top. Maybe you're asked the amount of heat, it goes from 40 to 120 degrees C. So 40, we can do this first line segment, then we do a phase change, and then up to 120. So we'd actually add up 3 line segments. So let's do an example problem to have a better idea of what this looks like. So what I did is I transferred this information onto a basic heating curve. And we notice that this is for water. So my freezing point would be 0 and my boiling point would be 100. I also gave you here the different heat capacities depending on the state of matter. And then we also know that delta H of fusion is going to be 6.01 kilojoules per mole. And our molar heat of vaporization is going to be 40.7 kilojoules per mole. So we're going to look at these different line segments. So if you'll notice, point A is at minus 60, point B is at 0, point C is also at 0. So I labeled the heating curve with different letters to make it easy to find our line segment amounts of heat. So if I look at line segment AB, we notice it's a calorimetry problem. So I'm going to do Q equals MCAT. I'm going to take that 50 grams from my problem statement, the heat capacity in solid form, and then my delta T is going to be 0 minus a negative 60, and I find that to be 6,180 joules. Okay, I'm going to change colors. So then the next line segment, we're going to go B to C. So B to C is a flat line. It is a phase change problem. So I'm going to take my 50 grams of water. I'm going to convert that to moles because I see the molar heat of fusion is in kilojoules per mole, and then I multiply by my delta H. So that ended up being 16.69 kilojoules. So now that I'm looking at this answer in kilojoules, I'm realizing that I should probably put these all in kilojoules. So that first one, if we divide by 1,000, is 6.18 kilojoules. Okay, so let's look at line segment CD. Notice we have a slope line. So we're back to calorimetry. So this is going to be our 50 times the 4.184. Traditionally, this is what we've used. And then my delta T is going to be 100 minus 0. So from my boiling point to the freezing point. So if I solve that one out, I found it to be 20,920 joules. So I can go ahead and convert that to kilojoules. Okay. Now let's look at line segment DE. Okay, notice that is also a phase change problem. So 50 grams, we're going to convert to moles like we just did, and then multiply by the molar heat of vaporization. Solve that out, and you'll find that that's 113.1 kilojoules. Okay, and then our last line segment for EF, where it's a Q equals MCAT. So again, it's 50 grams. And then we look at the heat capacity of gas is 2.03. This is between 120 minus 100. And I found that to be 2,030 joules, or 2.03 kilojoules. Okay, so to figure out that total amount of heat, we would actually have to add these all together. So it'd be the 6.18 plus 16.69 plus 20.92 plus 113.1 plus 2.03 to find my total answer, which I found it to be 158.92 kilojoules. Now, one thing I want to point out, notice line segment DE is really, really large, and line segment BC, it's not that big. So notice this would be line segment BC, it's not so big, but look at how big that line segment DE is. So when we draw a heating curve, the longer that line, the more heat. Okay, so that would be a long amount of heat, is a short amount of heat. Okay, so I do have this guided practice. It's a heating curve worksheet I've traditionally given. And here's some additional practice worksheets with answers and some videos to go with.